So welcome to the workshop on hardware, firmware, and software in wireless network by Dr. Venkat Viraraghavan. Dr. Venkata Subramanian Viraraghavan heads radio access software products for the network solutions and services unit in TCS Limited. He has nearly 2 decades of experience in telecom. He has worked as a physical layer architect for various technologies such as EVDO, HSTPA, HSUPA, LTE, and LTE Advanced. This includes numerous designs and implementation of real-time physical and MAC layer system on digital signal processors, as well as design and implementation of simulation models. He also worked on firmware, device, drivers, embedded OS, and an application software. Now he's leading the radio access network management software products with sustainability working group of Bharat 6G Alliance. He was earlier part of TSA research with interest in music and its relation to perception and emotions. He has over 30 research publications and patents and is a founding co-chair of Speech, Music and Mind, a satellite workshop of the Indus Speech Conference from 2018. Venkat Viraraghavan obtained a master's degree from the Department of Electrical Engineering, IISc Bangalore, and BTech degree from the Department of Electrical Engineering, IIT Madras, and recently completed the PhD at the Department of Electrical Engineering, IIT Madras. Without ado, I hand over the mic to Professor Venkat.
Okay, so as you would have seen since yesterday, right, we are exposing you to a lot of advanced topics straight away, right? So it's not that you should be able to explain everything. However, we have also alerted them about your background and what is it that you know, what you don't know. So a lot of the material has been designed so that you can consume it, right? They know that you have done ESTC, but you have not done electric net circuits and stuff like that, right? So you don't know what a Fourier transform is. All that they have been told. So you should be able to follow half of the talk pretty easily, right? And you should be aware of the second half of what is being done, right? And the aim is, over the course of the program, you will get to learn more and more of these things, and it's essentially to sort of educate you on what is being done. So it's my pleasure to invite Dr. Venkat Subramanian Viraraghavan for this talk. And as you might have noticed from the surname, we are related. He's my brother. Okay.
So thank you, Professor Janaki Raman. It's a pleasure to be back, a pleasure and privilege to be back at the alma mater. And I've been following how this course has started, and it's a wonderful course. I wish it very well. It's the best way we can reach to more and more people. So I'm best of luck to you all who have chosen to pursue this. So as he said, I'm going to talk about hardware, firmware and software in wireless networks because that is my current bread and butter. Typically communication systems, we start with Fourier transform and all that, but this has been tailored. What I want to finish with, I'll start with what I want to finish with. We'll do the last slide first. Okay. I want to be able to explain how these things happen in the industry. You don't have to worry about it at all now. Okay. But how do we get to this? We get to this in two parts. The first, I'm assuming, can we have a show of hands? How many of you know about frequency, spectrum, if not Fourier transforms? How many of you know formal Fourier transforms? Okay, that's a sizable chunk has not raised their hand. So we'll go with fundamental concepts. Those who know are free to contradict if you think something is not accurate. Okay, it's a very informal introduction, so I won't be surprised if something is, there's a little bit of hand waving. No, there's a lot of hand waving. There'll be some inaccurate statements. So those who know it, I'm happy to engage with them. So part one is conceptual. I'm pretty confident it'll be easy. Maximum you need is 12 standard. Okay. It'll be simple steps, simple logical steps. At least that's the intention. Part two will be a step up, but you don't have to worry about it. Like he said, no, it's just for you to get a feel for what happens. I would like to finish with how how this industrial, the industry implementations, how they are relevant to what you are pursuing. Okay, let's see if I can keep you from sleeping between now and 4 o'clock. So, the emphasis is on the word informal. So, whenever you get to your course and you start doing Fourier transforms or communication systems, if you do, you are not allowed to quote me. Okay? This is absolutely informal, made as simple as possible without using the word transform, but I will use the word bandwidth at some point. Okay? So, simple is the key word. It is a simple communication task. We want to convey one bit of information from one point to another, transmitter to receiver. The preference for online or offline classes. So, first thing I would like us to note is, it is simply a convention. Do you want to call online 1, offline 0? That is intuitive, but there is nothing sacrosanct about it. You can reverse it. But we are going with online is indicated by bit 1 and offline is indicated by bit 0. But how do you send a bit? It has to be some signal. So, we will start with again the simplest thing that we can do. Suppose I decide, again you will notice for bit 0, I am sending a square pulse. For bit 1, I send nothing. Okay? Again, if you have noticed, this is non-intuitive. So, if you have done digital circuits, this is like negative logic. Unfortunately, that is the convention in the communication world. Everything in 3GPP or 4G technology, 5G, 6G, bit 0 is represented by positive stuff and bit 1 is represented by negative quantities. Okay? So, we will also adopt the same convention, but it's only, both of these are just conventions. You have, there is nothing except that society has started using it, we better conform to it. Okay? So, I will send a pulse, simple pulse of a square pulse. The symbol period is 1 millisecond. This means I can send potentially a bit every 1 millisecond. So, that works out to 1 kilobits per second, 1000 bits per second. Okay. I know what I want. I know I want offline or online. I know. So, in the communication systems, we must abstract that out. We must talk only about bits as information or symbols to be sent. How they are interpreted is really not our concern. Okay. So, I want to send 0 or 1 to the other side. How will the receiver know which one it is? Any stabs, any guesses? How do you think we can do that? Yes, sir.
You have said that for 1 there is no pulse.
Yes.
For 0 there is a pulse. So if there is a pulse is coming, then it interprets that 0 is coming.
Correct. Can you expand on if the pulse is coming?
If the pulse is coming, then basically it is the amplitude is fluctuating between 0 to 5.
This is 1. For some reason, it looks like 5. A.
Yes, 0 to 1.
Ah, A. Okay.
So the amplitude will be fluctuating between 0 to 1, and if it is not coming, then
Okay. When you say fluctuating, no, is there a pointer available? I just wanted for this. Where am I? I see. Okay. Okay. One correction, if I may. Fluctuating means going this way. So, signal is not fluctuating in this case. It is just rising to amplitude A and it is held for a millisecond and then it drops. Okay. You have got the concept, but I am going to take it one level below in terms of detail. This is what I would like to do. Okay. Suppose we integrate this signal in that symbol period. So, integral of now y of t is what has been received. If y of t is 0, the integral will be 0. But if y of t is a, the integral will be output of the integral is a after we normalize by 1 by t. Okay. This is simple. So, if I get a at the output of the integrator, bit 0 has been transmitted. If I get get 0 at the output of the integrator, bit 1 has been transmitted. Fairly simple. Unfortunately, this ideal system does not exist anywhere in the universe. It looks like this. Okay. We will still integrate over the symbol period t, but now we can't expect it to be pure A or pure 0. It will be riddled with noise and we can't do anything about it. I mean, we can handle it, but we cannot say I want a system where there is no noise. The noise is typically a part of the receiver. Thermal noise is the biggest contributor to noise, but when we get to wireless systems later in the talk, interference is a big point, but it won't be relevant to us. So, either interference, so if you are using your mobile, and they happen to be in the same frequency slightly, you are connected to one tower and they are connected, both signals will interfere. That will also cause that pulse or that signal to change. What you receive will not be what is transmitted. First thing that we will get is noise. So, here when we integrate, we will get A plus some extra value. That is because we integrated noise. Don't think of that eta as a fixed value. If you do this integration 10,000 times, you will get 10,000 different values. On average, that will be 0, but it can be positive, it can be negative. Okay. What we are interested in is the root mean square of that value. That is telling us what is noise power. Noise power is, suppose I don't send any signal, what do I detect in the receiver? That's a simple way. See, this is one of those informal things I am saying. Don't use this as a definition of noise power in the course, but it's related to what you get when there is no signal. You don't send anything, what does the receiver see? That is noise power. So, the noise power is a receiver's property, typically influenced by thermal noise. Then, in this case, we can't say I want A at the output of the integrator or 0. So, we need a threshold. Now, we were talking about Professor Vittal Rao. So, he says, what can an engineer do? They will put a threshold which is between A and 0. So, we say A by 2, let us say. If it is above A by 2, after integrating, it is bit 0. If it is below A by 2 at the output of the integrator, it is bit 1. Okay? But that is not the ideal threshold, we will come to that a little later. Now, if you want to transmit multiple bits, so the sequence is at the bottom of that figure 0, 1, 1, 0. For 0, we are sending a pulse, for 1 we are sending no pulse, for another one we are sending no pulse, and then we are sending a pulse again. So, the convention, you need a convention here also. Everything is a convention, but we all must agree and stick to it. So, the convention here is least significant bit is sent first, and then the remaining in that, from that order, least significant bit onwards. So, we will talk about the start bit at the stop. Right now, bit 0 is 1, so signal goes down. In fact, they call it link idle. Link idle means no signal, that is what we also had done. All the other bits are 0 in this order, 1, then all zeros. So, the link is up, and then link, there is another stop bit which we will ignore, and then link goes back to idle. Can you keep this keyboard here and computer in IIT Bombay and connect by a wire? It won't work. So, the way we do it in communication systems is, I am going to jump lot of chapters and go straight to modulation. Okay. So, instead of sending a square pulse, we send sine waves. Okay. Let us assume that paradigm. If I want to send bit 0, so this is a sine wave. Okay. Now, I should get back the pointer. This is a sine wave that starts at 0 time, it starts like sine of 2 pi fct. If I want to send bit 1, I send negative of that, right. Now, since you had volunteered that time, will this integrator approach work for the sine wave? So, what? It's continuous is correct, but why is that not continuous? It had a jump at the end, but otherwise in between it was continuous only.
That is a constant signal, right?
Correct.
But this is not constant.
Yes. In fact, what property does it have? I'll go to the next slide. Oh, no. I have not written that down. If you integrate a sine wave over an integer number of time periods, you will get 0. So, the integrator is not going to work. You integrate plus a sine or minus a sine, you will get 0. So, we can say everyone has not transmitted a signal. That is what a receiver will say, but that is not going to be useful. Any quick suggestion on how we can get over this problem?
You can use amplitude modulation.
I do not want to go that far. Just look at it as a basic simple problem, puzzle. It is a puzzle. How can you get this information out? Frequency. That is also in complicated area by today's workshop. I will give you a clue. 12th standard, when you did AC, what is the root mean square of a sine wave? 1 by root 2, 1 by root 2. How do you get that 1 by root? Root mean square. So, simply multiply by sine 2 pi f ct. At the receiver, multiply by sine 2 pi f ct. If they have sent plus a, it will become plus a sine square. If they have sent minus a, it will become minus a sine square. Now, of course, instead of doing 1 by t, we do 1 by 2 pi a t. If you had done pi a t, you would have got plus minus 1. But I want everyone to remember that in 12th standard, we learnt 1 by root 2 is the root mean square of a sine wave. So, you will get plus minus half. So, this time when we have a carrier based, so this Fc is the frequency of the carrier. We are modulating that by, you can call this both amplitude and phase modulation. Its amplitude because you are changing it from plus 1 to minus 1, or its phase because it is changing it from 0 to pi. It does not matter. This is the square of the sine wave. It will add up to half if you integrate this after taking the square. Okay. Now, add noise to this. Okay. You will get that jagged sine wave, not a nice smooth one, but still if there is a signal, you will get the jagged sine wave. This is the square of that. That is, in what happens when there is noise, y of t becomes a or minus a sine 2 pi f ct plus noise, and then we multiply by sine 2 pi f ct. We do not multiply by noise, right? We just multiply by y of t by sine 2 pi f ct. Okay. Here, just like we had in the square pulse, we will get half plus eta, but I am calling it eta dash because this time it is noise multiplied by sine and then integrated. So, in random processes you will know what that impact is, but we do not have to get there. Noise multiplied by sine will give you an eta dash, some other value. It will not be half and it is not predictable. It will keep changing. It is random. For 1, the output will be minus half plus eta dash. This time, now there is a slight difference, right? Over there, in the square pulse, we said if the pulse is there, it is bit 0. If it is not there, it is bit 1. Here we have a little more information. I can say if it does not cross noise level, then there is no signal. They did not send me anything. If it crosses noise level, I will just look at the sign of that output. If it is positive, they have sent bit 0. If it is negative, they have sent bit 1. Okay. The threshold could be 10% of the signal power, but actually it should be a measure of the noise in the system. If you do not send anything and you do some integration after multiplying by sine, what do you get? That should tell you the level you expect in your receiver. So, you should tell the transmitter, please do twice that, 4 times that, so that we can reliably receive it. In this case, if we transmit multiple bits, you remember the same color scheme, blue is for 0, orange for the first one, green for the second one, and 0 for the red for the last 0. So, what are we saying? If it goes upward at the beginning of the symbol period, it is 0. If it goes downward, it is symbol 1. And so, this is 0, this is 1, this is 1 and this is another 0. You may notice that at these points the phase changes, but I am not going to get into the implication of what that means. Till now we have assumed there is noise in the receiver. What about whatever is in the middle? Especially in the context of wireless, the transmission medium, which is the air around us, plays havoc. So, we need to understand what the channel will do to that signal. When we transmit something, you can rest assured you will never get the same thing. It will always get distorted, it will get affected by noise in the receiver. I want to consider only the simplest thing. It is called attenuation. Everyone familiar with the term attenuation? So, the signal alpha is not the attenuation, actually 1 minus alpha would be attenuation, but the signal transmitted at some amplitude is received at amplitude alpha, alpha less than 1. This time key thing is what we receive at the receiver will be alpha by 2 after the integrator's output, alpha by 2 plus eta dash. It is not alpha by 2 plus alpha eta dash. See, the signal has come from the transmitter, the receiver adds the noise in its circuitry. If the transmission medium is reducing the amplitude of the signal, it will reduce only the amplitude of the signal, it will not reduce the amplitude of the noise. Noise remains as original eta dash, only the signal gets multiplied by alpha. So, in our receiver I said please send 2 times of my noise level. You should now measure what alpha is. If you want to tell the transmitter, please send, if you are so many kilometers away, send me this much. If you are 2 kilometers away, you can send less. Actually, that happens in a dynamic way in all your phones in 4G, 5G. It is called transmit power control. Both keep telling each other whether they should reduce or decrease their power. It happens every few milliseconds. Okay, but we will come to that in the wireless channel. Okay, in this case our threshold should be in such a way that after the attenuation it should not be comparable to eta dash, otherwise we can't distinguish noise from signal. You can actually, if you want to really look at advanced receiver techniques, you can detect signals whose levels are below noise. Okay, I am not saying it is impossible, but it is definitely not for 101 lecture in the series. Okay. So, we want it to be a good signal level. Now, I am getting greedy. Why should I send only 1 bit at a time in one symbol? I will send 2 bits. How can I send 2 bits? Here is one way. If it is positive, the first bit will determine, in these pair of bits, the MSB will determine whether it is positive or negative. So, here blue and orange are 0, 0. So, these two are positive signals. Green and red are 1, 1. So, these two are negative signals. The second bit, the LSB, is telling me whether it is full amplitude or half amplitude. Okay? Now, I have got 2 bits of information. I can send either it starts with upward or downward, and what is the amplitude.
But everything is negative logic, is it? Full is 0,
yes.
Half is 1.
The formula we use is simple. If you want to convert from bit to signal, 1 minus 2 times bit.
Okay.
When bit is 0, it is 1, when bit is 1, it is minus 1. Okay. Now, we have a problem when alpha comes in. If my signal is already become half amplitude, what was blue looks like orange in the receiver. I will say I got bit 0, 0 instead of bit 0, 1. So, we can't afford that. How will I detect this in the receiver? Receiver can keep on listening every symbol period. As soon as the first signal comes, we assume it is 0, 0. Correct? If you assume it is 0, 0, this blue will be known to the receiver as 0, 0. See, if you have x into y equal to z, if, or in this case, no, alpha into a equal to y. If you know a, you can get alpha from y. If you know alpha, you can get a from y. So, the pilot bit's job is to help you get alpha. First bit is always 0 0. So, as soon as I receive, I know that now I am going to expect alpha to be around 0.7, whatever this looks like. Okay. Then I can change all my thresholds. Earlier I had said it should be somewhere as 0.9 should be the threshold between high amplitude and low amplitude signal. Now I will say 0.9 times alpha. And how do I get alpha? Because I know the first bit is always 0 0, correct? Then I can adjust it for the rest. So, this will all be, the assumption is that the channel does not change so fast that it is alpha for the first symbol, beta for the second and so on. That is an impossible problem to solve. Even in the wireless thing, there are assumptions about how fast we move, how fast the users move, and that will determine how many pilots to send. Okay. So, this is the way we pack two symbols. Till now, I have been happily saying integrate over the symbol period, integrate over the symbol period. How do I know where the symbol period starts? Receiver does not know anything. I get up and click a button, it sends a pulse. I am not going to align to 0 milliseconds and click a pulse, it can come anytime. So, if the symbol, if this instead of multiplying by sine 2 pi fct before the integration, if we just shift by 1/4, we will get 0. Okay. So, we cannot integrate, use this integration method, multiply by sine and integrate, unless we know we are aligned. The other way you could lose alignment is through frequency. Now, you've got your kits. I think there are oscillators and 555s on that, right? You can generate oscillators using analog circuits, crystal oscillators and so on, right? But they are being generated by me in Chennai and someone else in Mumbai. Okay, that won't happen. It will be in this building and say someone else in that building, or the tower. Tower is using an oscillator. Your phone is using your own oscillator. It's not having some connection to the tower so that it can sync up. It's using, definitely they will not match. You cannot get exact frequencies. So, all communication standards prescribe a limit. So, we will be guaranteed that the tower will not do worse than 0.1 parts per million. That is the requirement. That means, if the frequency is 1 million hertz, actual frequency can be up to 1 million 0.1 and 1 million minus 0.1, whatever that is. That still does not mean it is 1 million. Okay? That is the range that that phone has to know. Within this range, I should still be able to correct that frequency. It is not possible otherwise, because whatever you do, if there is even a slight difference, it will accumulate, the phase will accumulate, and at some point it will look like the left graph. The phase will keep on accumulating. See, already this orange has moved a little to the left, correct? In these, because it is a 1%, 1% is 1 in 100, 0.1 per million is can't be visualized. But if you let this happen again and again, at some point this orange will, in fact, this difference itself, this correlation itself will be a cos wave. Cos wave with a frequency equal to difference in the two frequencies. Okay? So, you cannot let that, because if you happen to be at the point where the cos wave is 0, you will say all signals are not there, correct? So, you have to keep on correcting the frequency errors. The phase errors have to be corrected millisecond by millisecond in 4G and 5G. In 5G, you may have to do it 0.5 milliseconds. In 4G, all receivers do it every millisecond. Every millisecond, they must correct for frequency. Only thing they are guaranteed is, it won't be so bad that you cannot correct it. It will be plus minus 0.1 for a million hertz. So, this is, okay, what is the time now? 33. I think we are fine, because I had put a time check of by 2:30 I wanted to get to this point. So, what have we covered till now? First thing is very simple. Transmitter sends signals corresponding to bits. Bits carry information. Signals corresponding to bits are being sent by the transmitter. Receiver's job is, oh no, I need to do it in the presence of noise, in the presence of channel attenuation, in the presence, there may be delays, there will be a frequency offset. This is the minimum that a receiver has to do. Till this point, any questions? I am going to go to the next type of.
That previous slide you assumed that if that frequency thing is 0 0, then it already assumes that it is 0 0. But what if the initial frequency is not 0 0?
I didn't follow that. Say, what is it in this slide?
No, no, sir. Previous slide. Start with.
This one?
Yes, sir. This slide.
Ha.
You assume that
Oh no, it doesn't. Okay, I got your point. No, you imagine this picture starts from there. It can be half. No. Okay, now I got it. The transmitter must help the receiver. Receiver cannot do it if transmitter doesn't cooperate. Transmitter will, if you ask the transmitter to send 011110, transmitter will automatically add that 0, prepend that 00, prefix that 00 and send it. Okay? Transmitter won't tell you it's doing that, but it will add that 00. If you say I want this sequence 00011110, transmitter will still add one more 00. It will always do that 00. Both transmitter and receiver will use that and ignore it. The receiver will not give that first 00 to that consumer of the data. Whoever needs that bits, who needs those bits, will not use that 00. That will be between transmitter and receiver. Okay. So no matter what we do, there is always a probability of error in the received bits. So the first part we talked about was about signals and how signals can be affected by the channel, by receiver noise, and what the transmitter can do a little bit to help. Now the transmitter, we'll see, needs to do a lot more to help. The first point is, whatever it is, there will be some bits that are received in error. So how do we handle them? There are three ways of handling it. One, we should know, they say, if you know the problem, it's half solved. We should know that there's a problem. How do we know that some bits have gone wrong? That comes under error detection. Then, little more greedy. Can I know which bits have gone wrong? If it's all binary, 0 and 1, and I know which bits have gone wrong, I'll just flip them and I'll get my answer, right? Can I find out which bits have gone wrong? That is called error correction. In spite of all this, even you do error correction, after that you still have to do error detection, and we give up at the signal/bits level and say, this has gone wrong, this packet is wrong, we can't do anything about it. What do you do in those cases? What next when we know that a block of bits is incorrect? So we'll look at all these three one after the other. Error detection, parity bit. How many of you have heard of the parity bit? So I don't have to explain this in detail, right? I'll sort of breeze through it. The first time we add one parity bit for every byte of transmission, okay? And the parity is simply counting the number of ones in that byte. If that number of ones is even, you send parity bit 0. If it's odd, you put parity bit 1. Again, this is a convention. I don't know if this is followed. It could be the other. I think this is the way it is, okay? Because it can be implemented as a NOR, right? Now, suppose we get some bit wrong in the received byte. The red color bit is the one that has been received wrong, okay? What does the receiver calculate the parity as? It says, I got 4 ones, so parity is 0. And it notices that the parity bit sent by the transmitter is 1. So it rightly, that's why that cross is in green color. It rightly marks it as this byte has gone wrong. So it has detected an error in this byte. Similarly, for the other case, here parity was 0, but it came as 1 because bits flipped, 1 bit flipped. But you can guess by the nature of the definition of parity, if 2 bits flip, we can't detect it, right? First two bits are flipped in the top row, last 2 bits are flipped in the bottom row. Parity will say yes, 1 is matching 1, 0 is matching 1, that is why this tick is in red color. We think there is no error, but actually there is an error. It's wrong to say there is no error, it could not detect this. So there are some detectable errors, some undetectable errors, but parity is not the most powerful check. In fact, it's the basic check. A much more powerful check, which happens a lot in communication systems, is cyclic redundancy check. Okay, this is called CRC. CRC, how many of you know about CRC? Not this complex. This is CRC 302. No. Okay, then I'll explain it. I'm not explaining any of the polynomials. Okay, Andrew, who was here, is a punter at CR and error coding and all that. We'll error control coding and all that. So it works on a block of bits. It can be 16 bits, it can be 24. I have taken these numbers from 4G standard. It will be 16 multiples of 8 from 16 to 6144. Actually, it can go right up to 150,000 bits also. I believe with the latest specs, it can go even beyond that. Okay, but whatever it is, it takes a block, and in that block, it calculates either typically 8, 16, 24. 3G had 12 also. I don't think we use 12 in 4G if I am not mistaken, but it does not matter. If they use 12, they use 12. So, it can calculate a number of bits of the CRC. How does it calculate CRC? I am not getting into that. That has these polynomial definitions and so on. But the result will be, given an input of any size, there will be a corresponding fixed size CRC. If you give 6144 bits, you will get 16 bit CRC or 24 bit CRC. If you give 800 bits, you will still get 24 bit CRC. Okay. What should the receiver do? It decodes the block. It's got the signal corresponding to the block. Like we said, no, we'll have those sine waves of different colors. So it's got the signal corresponding to the bits in the block. From that signal, it will decode the bits. From the signal, it will detect the bits in the received block. From the received signal, it will detect the bits. From those detected bits, which are in pink color, from the detected bits, it will apply the same formulas and calculate a CRC locally. If the two of them match, then the packet is fine or the block is fine. If they don't match, then the packet is not fine. Okay. This is used heavily in wireless. The entire 4G, 5G, 3G, everything uses CRC left, right and center. They use it for small blocks, biggest blocks, everything. Okay. Different sizes of blocks have different lengths of CRCs. When you use YouTube video on 4G, it is calculating some 13, if you are getting the best data rate, no, you will get, it will be calculating some 26, 27 CRCs per millisecond. Sorry, that is only for the data. For the control, it will calculate a few more, but that we will not get to. Your phone has to do 48 decodes. At earliest version of 4G, your phone has to do 48 decodes per millisecond, but those will be small, not 6144 bits. If those 48 succeed in if any of those 48 succeed, it will try the big 6144, okay, but that is a separate detail. A 16-bit CRC, I got this from that. First intuitive thing is 16-bit CRC has a 1 in 65536 chance of going wrong. I mean, if you get exactly the same bit, but that is not true. It depends on the input and the length of the CRC. So, a 16-bit CRC will be able to detect 1, 2, 3-bit errors and some 4-bit errors. Okay. The higher the number of the CRC bits, the lower the chance of missing errors. However, I know that this is wrong, but I don't know which one is wrong. Right? It could be 10 bits that have gone wrong, it could be 1 bit that has gone wrong, but it's a 0-1 thing at this point. CRC matches, I'm okay. CRC does not match, it's not okay. So, can we do something about correction? And here I am going to gloss over this topic because it's not, I am not familiar with this. So, if any of you is watching Andrew's lectures, you can get much more info on this. But the idea is, if I send some bits and from those bits I send one common way is simply called repetition coding. Send the same thing 10 times, 0, 0, 0, 0, 0, 10 times. Then all 10 signals have to go wrong for that to go wrong, correct? It's unlikely. If you average over them, no, the chance of going wrong will reduce a lot. But repetition is very inefficient. 3GPP, the third generation partnership program which drives this 3G, 4G, 5G, 6G technologies, you won't find anyone more conjuice than them in terms of using bits. If you give a proposal which says, I want 1 bit more, you will get questioned 10 times. Okay? So, if you say just repeat 10 times, then instead of seeing 10 videos, you will see 1. So, we can't have an inefficient solution. So, we need to get more and more efficient solutions. That is obtained through adding redundant bits in such a way that I know some combinations in the input cannot occur. Then it will be easy to find out what has gone wrong. If I know some combinations cannot occur, I can locate the nearest combination. That's how I detect the error. If I know that I can send 000 or 111. So, let us take repetition coding. Instead of sending 10, I send 3, 0, 0, 0. And in the receiver, I have got 0, 1, 0. I can just use majority, no? I know that 0, 1, 0 is not possible in the transmitter. Transmitter would never have sent 0, 1, 0. Out of 8 combinations, 000 and 111, only 2 are valid. The remaining 6 are not valid. That is the principle of coding like this. You add redundant bits that will tell you which combinations are valid. It will reduce the space in which you have to search. Okay? Both original and redundant bits are transmitted, but wireless technology has sort of, made that very efficient. I don't want to get into that detail, but it calculates a lot of redundant bits, and depending on how good the channel is, it sends a little bit or a lot more and so on. It can adjust. Okay? If the channel is very poor, if your signal is showing just one stick, right, then it will send a lot of redundant bits. If your signal is showing 3 sticks, it will send very few redundant bits. Okay? Examples are here. All of them work, as you can see. I am not going to read it out. They belong to all the communication standards, and they will be in 6G as well. Shannon's theorem, if you have not heard of it, you can Google it. I am not getting into it. Okay, but it says such codes help us reach the channel capacity. If given a signal to noise ratio and a bandwidth, we can reach the capacity. That is what he has said. Like I said, we tried our best to correct, but still it didn't work. Then what do we do? Right? You sent a file, we did all this turbo coding, LDPC and all that, still it didn't work out. What do? You have only this option. You have to drop it at the receiver. Dropping is also a possibility. If you are speaking, speech is a kind of signal that we need to keep listening. Okay? You cannot say, please wait, I will retransmit and hold, right? That doesn't work. So, they will drop it. So, they will drop it in streaming cases. If you have missed that correctly at the point where Javed Miandad hit 6, if you have dropped that packet, you have dropped it. But for other things like file downloads, we want to do retransmit. Some retransmission happens for speech also. When it is faster than humans perceive, that much amount of retransmission happens, but not like file download. File download, if it stops somewhere, it can restart and all. That cannot be done in speech. So, at the transmitter, we send packet 1 and with it CRC, that is the yellow color. Receiver says, I got packet 1, based on my received bit, I calculated CRC, it is matching that yellow, so it is green. So, it sends an acknowledgement, we call it ACK. Okay. Once the transmitter gets the acknowledgement, it sends packet 2. Then the receiver says, oh no, I didn't get packet 2, CRC failed. So, the transmitter says, this time I will retransmit packet 2. Now suppose someone has removed the wire in between. Okay, then that's not a good idea because the ACK also will not come. Okay, but suppose there's a two-way channel, one of the channel has been removed, then it will keep sending NAC. So do you keep on sending two? We don't. That also has a limit. That is the design parameter. You can't keep on doing this, then your phone will do nothing else. So there are design parameters that will say how many times you can retransmit. Okay, and of course packet 2 second time it came out, right? So transmitter moved on to packet 3. But this is also inefficient. Why? Any guesses? Why is this inefficient? Good question, very good question. Someone asked this question long ago, so I'll answer it from the point of view of wireless channels. I told you about that repetition coding. So the repetition coding is used for those bits. So what happens is, these are heavily coded, just one bit, no? Sometimes 2 bits, 3 bits, depending on when we get to MIMO and all, but they are heavily coded. So it is very, very unlikely that you'll lose this. So in fact, all simulations of what is a channel performance when channel degrades and all that, usually will assume that ACK-NAC are fine. One of the things I was saying, right, even if signal is worse than noise, ACK will come out properly typically, because they'll give so much redundancy, but I know it's only ACK or NAC. Sometimes they do 6 bits depending on how much space is there. So ACK or NAC, yes, it can go wrong, but it is very, very rare because it is heavily protected in terms of this coding. But data we cannot do that, because then we will see one video instead of 10. Okay. In fact, you will not see a video at all, because you are doing it so many times, it won't look like a video if you do 10 times. Okay. What is inefficient about this? Yes. So I send one, it goes to the receiver does some processing, then it says CRC failed and sends me a packet saying in that NAC, small NAC packet, it says NAC. After that I can send 2. But we don't design a system where 90% is going wrong. We want to design a system where 90% is fine, right? 10% is a practical limit that people use for what is known as HARC retransmission. If it up to 10%, definitely up to 5% errors, the transmission can survive. So if you're going to expect ACK 95% of the time, why keep on waiting? Just keep sending. First 4 packets send whatever happens. Okay? So I have not lost any time now. No waiting. Because at the time of transmitting 3, receiver is finished processing packet 1 and it has told me ACK. Before transmitting 5, I will check. Oh, that has come as ACK, I can go with 5. Before transmitting 6, I will check what has happened to packet 2. At that time, I recorded that the NAC has come, so transmit 2 again. So you see the number of retransmissions will be proportional to the number of NACs. That was true in the previous thing also. How many retransmissions depends on number of NACs. But all the gaps in between have been filled in this sliding window request. Okay. So after 2, next I want to check packet 7. The next packet to be transmitted is 6. I will check before 6 what happened to 2 packets, what happened to the previous packet. So packet number 3, was it ACT? It was. Then I can send 6. Okay. Now I wanted to observe the sequence number. Who gave you the sequence number? Sequence number has to be added. Transmitter has to add a sequence number, receiver has to check the sequence number, and it has to send the ACK information can be controlled just by the timing. It won't send the sequence number in the ACK, but it will send it by timing. Okay. This sequence number, that 0, yes sir. It adds it to the bits. Earlier he asked the question about if I want to do 00, 01, 11, 1011, transmitter puts a 00. After that 0, 0, that is for the signal. For the bits, it will put a sequence number in front. Transmitter will put the sequence number without telling you. Receiver will use that sequence number. It won't pass, neither will it pass that signal which is helping you to get the start of the transmission, nor will it pass the sequence number which it has got there. But these are overheads. These are called overheads. You cannot avoid them. If you want to transmit 10,000 bits, you will have 100 bits of overhead. First, you have to send, I have space to transmit 10,000 bits. Straight away, that code block size was 6144. So, straight away 24 bits will go for that. Out of 10,000, I have got only 9776. Then I am adding some 10-bit sequence number or 16-bit sequence number. I have gone to 9760. Then I want to add some ACK information, another bit, it will become 9759. Then I want to make it a multiple of 8, it may become 9752 or 54 or whatever, right. So, these overheads will keep eating. Total capacity available includes all of this. So, we cannot escape it. So, it adds those sequence numbers and increases the overhead. So, here this is a good time for us to get into this OSI model. How many of you have heard of the OSI model? You must have seen it, right. So, I will take very little time. Actually, like he read out, my experience is here, signals and bits and a little bit in data link. Rest of it, I have not worked on it directly, but I have enough to tell you about it. I have seen enough to tell you about it. So, the physical layer is working at the levels of signals and bits, signals to bits and bits to signals. The data link layer, at least in terms of a networking concept, is two things that are connected to each other physically. It can be air also, but it is a wire connection. This much happens at the data link layer. But suppose I have a network in this department and a network in some other department. Within the department, it is like data link, but department to department, you need the networking layer. It allows you to talk across networks. Your Wi-Fi network at home and someone else's network, if they are not routed, you cannot talk to them. But if you can send packets to each other if you are all connected to the same Wi-Fi. I do not know if you have tried that. You can ping at least. Yes, sir. Telegraph. I have not thought about that. It is like a data link layer, yeah, because it is a connection. So, the signals are basically the pulses that we said. Length of the signal makes a difference is the information. But there also they had human routing, no? People used to sit and route. It is not software routing, but people used to route. So, you could send a telegraph to someone, they will forward it to someone else. So, networking is also possible, I think. That is not a rigorous answer, but we can think about it. Yeah. Oh yes, so good point. I just counted to 9752. No, CRC I told you, right? 24 bits are gone. So, we have to transmit that. Of course, otherwise how does the receiver compare? It is, yeah, MD5 checksum is not used. It is you, I do not know why, but I suspect it is either because of the way the checksum is calculated, you need to tell each other how, or it is too much complexity. CRC may be easier to calculate. Does not matter. See, that we cannot distinguish. You have to repeat the packet. Only if you dig into that, you will know that packet came correctly, but CRC got wrong, and you feel, oh, what a pity, why did we retransmit this, but you can't do anything about it. If the CRC goes wrong, you transmit the packet. No, I am not saying that. The transmitter, if it advertises a frequency of 2.1 gigahertz, then 0.1 ppm is what? It can go to some 100 hertz or 200 to 30 hertz, something like that. Its frequency error will not be more than 200 hertz. That is what it means. It does not mean it is exactly 2.1. Okay. So, this is the network layer. Yeah. Transport layer has got something called QoS. It does segmentation reassembly of packets, because the application, the sessions, so when you open a browser session, it operates at this layer. But underneath, it uses a transport layer, which is like TCP or UDP, which itself either uses the Ethernet cable or the Wi-Fi or your data. So all that come under this network data link in physical layer. The QoS, how good should that quality be? So the nice thing about 3GPP is they have, I forgot the full form of QCI. I think QoS controller channel. We'll have to Google it. It's an indication of the QoS. Okay. So this QoS, there are 9 QoSs or QCIs defined in 4G and a few more in 5G. The QCI number 1 is for voice. When you've heard of VoLTE, voice over LTE, that uses QCI number 1. When you use video over LTE, that uses QCI number 2. Any guesses for what QCI number 3 and 4 are? I'll leave 3 and 4. 5 is for signaling. To set up a voice call, you need QCI 5. 6, 7, 8 are for browsing data calls. What is need? 3 and 4 are for, you can imagine how big that industry has become. 3 and 4 are for gaming. So if a mobile and the network understand the gaming applications, they will set up QCI 3 specifically for that, because you need very quick response. The latency has to be good, data rate need not be very high, but it should still be good. So if you want gaming, you need to use QCI 3 and 4. This is the point I wanted to say. Layer wise headers. So every layer here will add its own sequence number, its own information, protocol information. In IP layer, you will add IP address. In lower than that, you may have MAC address, but if you go through Ethernet, otherwise you go through Wi-Fi, it will have its own 4G, 5G will have their own network data link. So every layer will keep adding overheads. Okay. Layer wise headers and parity bits, I am calling them parity, but it can be CRC, whatever, are necessary overheads of communication. Okay. So I said packets should be detected, corrected, retransmitted or discarded. Network layers retransmit packets that are discarded. So if a lower layer misses and says I have given up on this packet, you transmit at the higher layer. It may have come from some big file, part of that file failed, you made it into FTP protocol already makes it into chunks, I think. It will retransmit that chunk if something below that fails. Okay. I'll breeze through bandwidth. Anyway, we are not going to look at Fourier transforms. So this is not a good place to start since we've lost time. I'll go to this. This is some unit called decibels. If you don't know about it, forget it. No problem. That number is important. You can see this black arrow and this one, they are different scales, different Y scales are approximately 25 dB. This corresponds to the square pulse and the sine wave. If we transmit this on a wireless spectrum, we will be jailed for infringing on other operator spectra. This 25 dB is hopeless for wireless transmission. So we will come to that later. But if you see any communication textbook, we work with what are known as band limited signals. So this square pulse and the sine wave with a square windowing effect, they are not band limited. They go on forever. Okay. But we need band limited signals, and the way to do it is actually force using filters and all that, you force band limiting. But communication systems assume band limiting. There's a concept of positive negative frequency, we can skip that. How much it occupies in frequency is the bandwidth. Okay. Now this bandwidth is a key constraint because it's not available for free. Now let's assume we have some bandwidth for communication. How do I get multiple people to use that bandwidth? It can be like this. Each, that looks like the sorting hat from Hogwarts, but each hat is for one user. Okay. Blue, dark blue, orange, green and light blue. This is called time division multiplexing. Each user gets a different slot, but they use the same frequency, same location in frequency, same bandwidth. You can guess what is frequency division multiplexing. They all transmit together but they use different frequencies, center frequencies. Okay. A mix of these two is what happens in 4G, 5G, 6G. It's called, if you don't like this slide title, you ignore it, but it's called orthogonal frequency division multiplex, multiple access. Different users get different frequency bands which are orthogonal to each other. So, that is what helps receive. If they are not orthogonal, we cannot receive it, and they are simultaneous. So, this picture, if you remember, that will be enough. This is what is a typical time frequency grid used in 4G, 5G. I have not given the units, some of them are, this is more or less like 1 millisecond. You will not find this anywhere in the standard, but you can construct it from there. So, you can see different users. So, the same user is getting a chance later, correct? This green is getting a chance a little earlier. So, if it is a voice call, for example, they will not give you much frequency. Voice does not require so much bandwidth, but it requires regular bandwidth, regular chance to speak. Your signal should go every 20 milliseconds, otherwise you will feel the other person is not there. So, that is what the QoS is. QCI 1 will ensure you get a chance every 20 millisecond, but not for so much data rate, just that much. Okay. The lowest possible is assigned. In fact, when we do the measurements, when we run only VoLTE calls, nothing will get used in terms of bandwidth, but it will keep getting used periodically. When we run a 10 GB file download or something, the whole thing will get used, all the bandwidth will get used. Okay. So, this was 250, we are still catching up. So, bandwidth and carrier frequencies are key resources that allow multiple users to connect simultaneously, and that allows us to come to wireless communication. Okay. Electromagnetic spectrum, this I think is allowed. A small part of this, if you can see it, our amplitude modulation radio is somewhere here. FM is around this 1 meg, 100.1, 98.4 or whatever, no, 98.6 seems like temperature of human body, but whatever, 104. So, that all happens here. Just above that is TV, then comes our 2G, 3G, 4G, 5G. So, I will expand into that in this part of the question. Spectrum is a critical resource, and because of the scams that have happened, it is a very famous resource also. Spectrum is a critical resource shared according to who is using which carrier frequency and how much are you reserving outside. You remember that picture of that triangle? How much around that center are you going to use? So, each operator in different states, they get different locations as well as different amounts. I do not know how to stop that. Okay. So, the other point about wireless is transmission medium is air. So, we will go through very quickly. Without a wire, what do you mean by path? See, if I know a wire is there, signal flows through that. What happens when there is no wire? Everywhere. Answer is everywhere. It is all over the place. So, we will find out what those characteristics are, and of course, in this case receivers move. Your mobile, that is the whole point, it is called a mobile, no point sitting in one place. So, just some conventions. Typically, the way we cover, way an operator covers is, this is the ideal. We rarely see something that is exactly like this, but each antenna has a beam width of 120 degrees. You can assume it that way. So, they put 3 antennas on the same tower. Each of them is like an independent cell, it is called a cell. Whatever we discussed, I showed you one graph of time frequency, every cell has its own time frequency resource. Okay, you can do simultaneously. Cell edge, there will be interference. I said, no, your phone is connected to that tower, that will happen at the cell edge. Just something, the transmission from tower to mobile is called downlink, from mobile to tower is called uplink. There are multiple towers, but we will not get there. I will just go very quickly in spectrum. This is what happens. So, sometimes we use different frequencies for uplink and downlink, but at the higher frequencies we typically use them together. Same frequencies for uplink and downlink, but that time you have to do time division. It is called time division duplex. I am sending now downlink, After I finish, you send me uplink, both in the same frequency, or I am sending here downlink, you send me here uplink. Okay. So, this is the kind of spectrum that we use. Your 2G starts from this band 28, band 5. You can approximately look at it as 2G is here, from here is 3G, this is 4G, 5G goes to 3.5 gig, which is not in this picture. 6G can go even higher, 25 gig. So, it looks approximately like this. Maybe we do not have to spend too much time. As the carrier frequency increases, the range comes down. Okay. We will not get into that. So, 3.5 gig or 3500 meg is 5G. Above that is, you can call it 6G, but the frequency I keep hearing of is 144 gig, 144 point something gig, but that is not yet fixed. 6G is still evolving.
What's the range of FM?
It must be much higher than this. It could be, because it is 100 meg, right? Yes. I do not know why I had this slide. We will, no, we will skip it, we will skip it. Oh yes, yes. I said that blue will be a pilot now. How often do you need the pilot? You need 3 to 5% overhead. Pilot has to keep repeating in a wireless channel, because the user keeps moving. So, you cannot, in a wire line channel, I can send the pilot once and keep transmitting for 20 minutes. I can't do that. 4000 times a second we must send the pilot in wireless. Okay, that turns out to be, it does not occupy the full spectrum. So, it turns out to be some 3 to 5% overhead. This we talked about. Multipath, if you have heard of Young's interference experiment, it is more or less like that. Different distances traveled by different paths, different reflectors. So, these are reflectors will result in a different phase at the time it reaches the receiver. All those will combine either destructively if you are unlucky, or constructively if you are lucky. So, when it combines destructively, it is called fade. That is what a channel fading means. Okay. I do not want to get into this detail, I only want to motivate one thing. One way of overcoming that fade is having two receivers, slightly different. The distance depends on the wavelength of the carrier. In that case, both will not fade together. If one of them is destructively adding up, interfering, the hope is the other is also not doing at exactly the same time. So, this is one way to do it. The other way is to do both transmitters, only one receiver. Again, it won't, but here you need some encoding of the stream. But what we really want, which is something that is happening in 4G, 5G, 6G, is suppose I put multiple antennas and multiple antennas at the transmitter and at the receiver, then the number of transmitter receiver combinations is NT times NR. If I have 4 antennas and 4, now I have 16 paths. 16 paths I do not need to use only for redundancy. There is a way, if these combinations are uncorrelated, that is the key. If they are correlated, you can't do anything. If they are uncorrelated, we can increase the data rate. Okay. That is what this point is. The number of independent layers of data depends on, it cannot, you can, if you have 2 transmitters, 1 receiver, I can do only 1. If you have 2 transmitters, 4 receivers, I can do only 2. But it also depends on the rank of the channel matrix. So, I thought I will put one complicated equation in this whole thing. It just looks complicated, but it depends on the rank of this matrix, how good your channel is at that time. If this is not invertible, you cannot have NT streams. Okay. That is why it is called the rank. This rank matters. The layer number of independent streams is dependent. If you have a good channel, rank is good. For 4G, 5G systems, you can do 4 times the rate, 2 times the rate. So, if you move from 3G to 4G, just because of 2 cross 2 MIMO, you can get twice the rate. So, here are some parameters. If it is getting recorded, then maybe you can just have a look at it at that point. We will go to, okay, I am going to skip this part, okay, because I do not think we have the time for it. All I want you to see is The channel that is the workhorse of the 4G, 5G is this thing called PDSCH, Physical Downlink Shared Channel. It carries all the heavy traffic. You watch YouTube, you also watch YouTube, you use Amazon Prime, Netflix, all of them go on this only in the downlink. Okay, we'll talk about downlink, not so much uplink. But just to make that, make that work, we need so many other things. What are the things? All the things that we studied earlier. You need something for timing, so you need to send a sync signal. You need something for frequency error, and you need something to estimate the channel, so you send the pilot, which is cell specific reference signals. Then you wanted retransmissions, so we send the PH channel. Then you wanted to do MIMO, so we need that PDCCH to say, are you sending 1 layer, 2 layers, 3 or 4? And then on top of all this, we need the hardware that will actually transmit that signal. Transmitting a signal over 1 kilometer is no joke. So we'll come to that part. Okay. Now we did this picture. Collapse all of this into, this is called the radio in the physical layer. We talked about the physical layer. On top of that, you need MAC for retransmissions. It uses the same PH in the previous slide. Then you need RLC to segment and combine. And then you need PDCP, which talks to the IP. So when you get IP packets over a network, it is this layer that converts it to packets that can be transmitted over wireless or the other way around. Then to control this, you need something called radio resource control and then radio resource management. Who decides when I move from one tower to the other? All that is done in what we call the E node B or the G node B. There is a protocol stack view. I wanted to go there, but we can skip it. Okay. Whatever I said is an E node B or a G node B. It's called an E node B in 4G, G node B in 5G. You can imagine it as everything that is on the tower. That is not enough. Who is going to route that data back to the YouTube server? So you need mobility management entities in the core. You need serving gateways. You need packet gateways, and you need some DNS which will connect to the IP. Then you need subscriber services. How do I know whether I should allow this phone or not? You need subscriber services. You need policies. Is this person meant to get 2 Gbps or 1 Mbps? 2 G per day or 1 G per day. That is in the policy. Then there are so many other things. In the core that we deployed, there are 31 components. Okay, I have talked in the packet core, I have listed only some 4 or 5. There are 31 components that go into this. Okay. And apart from that, we have something called management. See, one thing we should realize, when the number of things scale up like this, just managing them is a big headache. If we don't design them for managing proper management, it will be impossible to run a network. Okay. So this OAM, it's called operations and maintenance part of the code that runs in every element, is very crucial as you start scaling up. When you make 1 unit or 10 units for the lab to do your testing, it doesn't matter. You can just log into the SSH shell and run. You can't do that. When I say, oh, you have to climb that hill because this tower is on top of that hill, will you go there? You have to make sure everything is remotely accessible. I should be able to do everything with one visit to that place. So this OAM is an underrated but very important component of any industrial production grade product. So if you put them together, it looks like this. The complexity of the E node B and the core around it. Now you put the complexity of the IP network around it, and it will become mind boggling.